He is a winner of the National Science Foundation Career Award and the Dean's Award for Teaching Excellence in the College of Computer, Mathematical, and Physical Sciences at the University of Maryland. His current research interests include empirical methods for identifying and eliminating bottlenecks in industrial development processes, experimental evaluation of fundamental software engineering hypotheses, and development of tools that demonstrably improve the software development process. I said that all without stuttering. Oh, we're not done yet, right? And Atif Memon, I came close. I tried. Yeah. Is an associate professor at the Department of Computer Science at the University of Maryland. He was awarded the gold medal in, wait a minute, what is this? All right, I'm going to skip that part. Well, because what it says on my paper is you were awarded the gold medal in BS.
When you're a professor, you have.
Well, all right. He was awarded fellowships from the Andrew Mellon Foundation for his PhD research. He received the NSF Career Award in 2005. His research interests include program testing, software engineering, artificial intelligence, plan generation, reverse engineering, and program structures. He's the inventor of the guitar model-based testing software. So let's welcome Adam and Atif for the Skoll Distributed Continuous Quality Assurance System.
Okay, thank you. As Alan said, my name's Adam Porter, and I'm sorry, but you're gonna chain me to this table, guys, aren't you? Okay, so I'm not used to that. I usually move. All right, so my name is Adam Porter, as Alan said, and today I'm going to be talking. I and Atif, my colleague Atif, will be going to be talking about some work that we've been doing, looking at something that we refer to as distributed continuous quality assurance. Now, as we've heard, many times today, under pretty much all measures, software systems are getting larger and more complex. It's quite common today to see systems that run over numerous platform, compiler, and library combinations. They've got tens, hundreds, even thousands of configuration options. They evolve rapidly. They're incrementally evolved, sometimes by geographically distributed development teams. They often sit on top of and run in concert with other systems that are equally complex and are equally changing on their own rapid and unpredictable time schedules. And then finally, the notion of what quality is or what we're trying to test for is actually multifaceted. It's not just functional correctness, it's reliability, availability, compilation time, memory footprint, it's all these things. So we were asking ourselves, well, how should you think about doing QA for systems like this? Because some of the, at least in our opinion, some of the best practices, things like continuous integration and test-driven development and these kind of things, and I think this sort of, Patrick sort of hinted at this earlier today too, weren't really designed for this sort of, system with high configuration complexity. Okay, they're really built for a little bit different, different scenario. So what we've sort of come up with is that we're sort of envisioning changing or redesigning traditional QA processes so that they'll be run around the world, around the clock on powerful virtual computing grids. Those grids might be end-user machines. They might be all the computers in a project-wide intranet. They might be run on a dedicated cluster. Any of those will work for us. And so what we do is we've sort of looked at various QA processes, various testing and performance measurement tasks, and we've redesigned them, generally by looking at how we can chop them up into millions of little pieces, and then start distributing those pieces intelligently to remote clients who are out in our grid somewhere. We're going to do that one at a time. And now, as those results start to come back, we're going to be merging and analyzing those incremental results and trying to use that insight that we're gaining on the fly to steer the process to complete it in the most efficient and effective manner. Now, why do we do this? I think it's fairly obvious. One is, through massive parallelization, we think we can do a lot more QA a lot faster. We also think we can do better QA. Okay, we can, by involving community resources in our processes, we can capture or use at least resources and environments that we don't have in-house. Okay, we might have our lab might have certain things in it. Our community may have other things. By pushing work out to our community, we can essentially borrow those different resources and configurations, at least for a time. Finally, it's also, this model gives us a chance to use better algorithms, I think, that coordinate QA effort and share results across this large grid of computers in a way that's going to enable us to do more sophisticated and deeper kinds of QA. Okay, we're doing this work. I'm here talking about it with Atif. We're doing this with lots of other people, people at Vanderbilt, Georgia Tech, University of Nebraska, the National Institute of Statistical Sciences, and other folks at Maryland, and we're looking for more people too. So we're always interested in partnering and collaborating with other folks. I think these problems, as we're starting to see this use of large-scale QA going on, I think we're opening up lots and lots of interesting research challenges, and there's a lot of work to do in this area. Okay, let me do a little bit of sort of a review of some of our work in this area. So we built a system that we call Skoll, and it's an infrastructure, and it's also an approach for implementing and executing these DCQA processes. So let me kind of give you the high level view here. Basically, really simple here on the let's see, I guess on your left, on your left you've got the Skoll infrastructure. It's got some things in it. On the right, notionally, we've got our grid of computers out there who are going to be able to run these jobs for us. So when we ask ourselves how do we use this grid, how do we use this infrastructure to do QA, we've come up with a basic approach in which we start by modeling what we call the configuration space, okay, or the QA space, all right, which is, you can think of this as a giant list of configurations in which you're going to want to do some kind of testing. Okay. Now, typically that list of configurations is enormous. It's too big to actually work with in its entirety, and so we're going to have to find ways to selectively visit or selectively test, or whatever it is you're going to do, individual points in that configuration space. So that's one of the big challenges. Is how do we do this sampling? How do we reduce the size of this configuration space to something manageable that can fit into, let's say a continuous build process or a nightly build process? So there's going to be this part of where we develop these algorithms, and these algorithms are going to go into our planner component, okay? And when we're ready to start the process, the planner will basically fire off or schedule the first, one or more initial jobs to do. Okay, at this point, we're now ready to accept work from our clients. So our clients start to call in and say, hey, I'm out here, I'm a Linux box, I'm a Windows box, I got this compiler or whatever it is. What would you like me to do? Okay, so the server's going to look in the database and say, well, here's the jobs that are outstanding or pending. You can run, one of these. It'll pick one, okay, and it'll give the client. It'll basically look in the database, grab the task list, grab whatever source code or build instructions, whatever it is we need, package all that up and send it to the client. Okay, the client's going to take those instructions, take that software, build it, test it, whatever it is we're going to ask for it to do, and it's going to send us, it's going to do that and send us back the results. Okay, so now the server's here, it's sent out some jobs, work comes back, results come back, and we're going to take that feedback, we're going to stick it in the database, and we're basically going to trigger the planner and say, hey, the state of the world has changed. Take a look and do something if you need to. All right? And so we can basically use the incoming results to kind of steer the process. And I'll give an example in a minute of one way in which we can do that. Okay. So again, this is a little bit of a review for anybody who was here last year. I talked about this little part, and I'm just going to do it again as a review, and then we'll get into some more recent things after that. But some of the work that we did originally with this project was basically applying QA to a project called ACE, DAO, and CHOW, okay, or ATC for short. So this is a 2 million line open source Corba implementation. It's maintained by even more than this now, but more than 40 developers, core developers, distributed around the world. There are 20,000 users worldwide, more than that. It's a product line architecture. It's got 500 different configuration options. You can compile things in, compile them out, turn policies on, set them at various levels, optimize this, change OSs and compilers, et cetera, et cetera. Okay, so it's exactly the kind of system that we think is not well handled by today's current QA methods. At peak times, it's evolving at a rate of something like 200 CVS commits per week. Okay, which is something like on the order of 1 hour. I'm sorry. And they're interested in lots of things besides just functional correctness. They're interested in quality of service, footprint, compilation time, all these other things. Okay, so again, following our model, the first step we need to do here is to define a model of what our configuration space or our QA space looks like. So this is just a piece of it, but just to give you an example, we want to capture information about the kinds of compilers we can use. There are some compile time options that talk about what is compiled into the system and what is compiled out of the system. Okay, so they've got embedded versions where lots of stuff is left out. They've got more full-scale versions where lots of things are compiled in. We've got runtime options, various kinds of policies and optimizations that can be set. For example, this org collocation basically says when two objects are considered to be in the same orb and thus can talk directly instead of talking over the network. And that can be on a global basis, on a per orb basis, or all objects are considered to not be co-located. The system is made up of a couple components, ace, dow, and chow. We can talk about which components we want to configure into our test system. Also, there are a number of test cases for the system. Not all of them run under all configurations, so we have to define parameters that tell us which configurations which tests can run in which configurations. Finally, we have this list of options and settings, but not every setting can coexist with every other setting. Okay, so we also define constraints over these options. We say, well, look, if you want to compile in AMI or asynchronous messaging invocation support in a particular configuration, you must also you must be on a configuration that has more than the minimum Corba features enabled. Okay, which this is not DAO's minimum Corba. This last constraint says that if you want to run the ort.runtest, runtest.pl test, you must be on a configuration that has more than the minimum Corba features installed. Okay, so this sort of sets up a space of possible configurations. If we don't, all the configurations that don't violate any constraints are valid configurations, and that's effectively the QA space in which we want to do our testing. Okay, so let's take an example. We've got this model, okay, and now we want to go about testing configurations in that space. So let's take a look at this. This picture here. Now this is this is actually based on real data, but it's only a part of the full space. Basically, every node in this graph represents one valid configuration. Okay, and I've drawn an arc between every two nodes or every two configurations that differ in the setting or the value of exactly one option setting. Okay, so basically, if I have a line between two configurations, they're nearly the same. They just differ in the value of one setting. Okay, and we'll show you how we use that in a second. So let's say we start this process, client comes in, says, I'm ready to do some work, what can I do? And we give him this guy down here at the bottom, right? Here, take this configuration. Client builds it, says, compiled fine, sends us back the results. Great. Second client calls in, says, I'm ready to do some work. We give him this one, hey, everything's fine. Same thing here. Now the fourth guy comes along, and we're just randomly grabbing configurations at this point, and we give this client this configuration, and it comes back as failed. Okay. Well, now what we can say to ourselves is, gee whiz, let me stop randomly jumping around in this space. Let me zoom in on the area in which I've observed a failure. Okay. So what we do is we compute all the distance one neighbors of this failed configuration, and we make those high priority tests so that if a client comes in and can run those, that's the next one we're going to go with. Okay, and you can see how this is going to play out, right? So we start to test those. If those guys fail, we'll make their nearest neighbors high priority, and we'll keep spidering out until we run into places where we don't fail anymore. Okay, and we'll stop there, and we'll go back and look at the other things that are still pending in our high priority queue. And then you can see this will just keep going. And what you end up with here is that in this case, we pretty quickly find a border. All right, we find a border here between the configurations that pass and the configurations that are failing. Okay, and so now an obvious question then is, well, is there anything we can learn about these configurations that would help us to explain what these red dots really are? Right? What's interesting about these configurations that would explain why they're failing? So one technique that we use, and you could use lots of others, is to use a machine learning technique called classification trees. We feed it this data, and we say, fine, tell me, if you can, is there anything interesting about these failing patterns? And again, this is real data, but what we found on one particular release was if Corba messaging was disabled, if AMI support, asynchronous messaging invocation support was disabled, we got error message number 3. Okay? If Corba messaging was disabled and AMI was enabled, we got error message number 1. If corporate messaging was enabled and AMI polar was enabled and AMI callback was disabled, we got error message number 2, and everything else passed. Okay? And then we could give this information back, and we did give this information back to the developers, and this helps them to say, well, okay, I don't know exactly what the problem is, but I know it exists in these configurations and not in all these others. Okay, so it's an attempt to try to help give them whatever information we can to help them get to the root cause of the problem as quickly as possible. Okay? Okay, so that's a fairly simple example, and hopefully it gives you the flavor of what we're doing. What I'd like to do now is talk a little bit more, again, just a little more depth, some of the more recent things we've done, that we've tried to invent some more novel and interesting DCQA processes, and then I'll talk also about some of the, we've done feasibility studies for these new techniques, and I'll tell you a little bit about what we found out. I'm going to talk about 3 things today. The first one is going to be focused on build testing for component-based systems. The second one will be like the problem we just talked about, trying to identify or understand configuration-related faults, and understand what's causing them. And that's going to be a little more functional testing, more than just building, but functional testing also. And the final thing, I'll turn over to Atif, who will talk about some work he's been doing to actually generate the test cases themselves. So right now, our early stuff says, project, you want to use Skoll, you give us the test cases, and we'll figure out a way to run them for you. We'll help you run them. And Atif's saying, well, if we're going to start automating the running of tests, and lots of tests, then the human test writer becomes the huge bottleneck here, right? So he's working on techniques that, at least for some cases, will allow you to automatically generate a test, and then we can run them. Okay. All right. Let's go talk a little bit about build testing. So basic problem is you've got a system that's built out of a bunch of components, and you want to determine which configurations build and which configurations don't. Okay, and so configuration in this case means which components and which specific versions of those components can you hook together and build, and which ones can't you. So our approach, again, following our general model, is we're going to model the configuration space. We're going to find ways to sample that configuration space. We're going to test that sample. Okay, and we're going to analyze our results to try to identify where the failures are occurring. Okay. And by the way, I've got down here just some pointers to some papers if people want to read more about some of this stuff. Okay, and those will be on the slides when they appear. Okay, so our guinea pig for this particular process is a project called Intercom, which was being done at the University of Maryland. Basically, Intercom is a middleware system that allows you to hook together components that do simulations of physical processes. So radiation in this generation of radiation at the sun. Radiation travel through the ionosphere, et cetera, et cetera. So you got all these components that do various things and simulate various kinds of physical processes, and Intercom allows you to hook them together simply to create larger, more complex processes that would look at bigger phenomena. Okay, this particular system is built from up to 14 other components. Okay, each component can have any number of actively managed versions. Okay, and you've got complex constraints among these configurations. So the developers, what they'd like us to help them do is to identify the working or the broken configurations. They'd like us to help them understand how they can broaden out the working set so more people can use their tools, okay, instead of having things crash out of the box. And they also hopefully can use the stuff that we're doing also to kind of make some decisions about where to put their resources, where to prioritize fixes to specific components, or which things to let go, or this kind of stuff. So, okay, so what do we do here? Again, basic approach here. We're going to start with a model of a configuration space. This particular model is something called an annotated component dependency graph, or an ACDG. It's got 2 parts: a CDG, which is a component dependency graph, and a second part, which is a set of annotations. Okay, so boom. All right. Let's take a look at that. Okay, so what have we got here? This is this picture at the bottom represents a CDG for this intercom system. It's made of 2 different kinds of nodes. You've got component nodes, like this one that says, you probably can't read this, but the one that says IC, PVM, AP, MCH, LAM. Those are the components or the packages in this system. And they're hooked together by relation nodes, right? So the IC depends on PVM. The ones with the stars are PVM and AP, and it turns out those are some compilers down there, okay? There's also some ORs. So, for example, AP depends on some things, and either MCH or LAM, which are both implementations of MPI, okay? So we're going to capture these sort of gross level component dependencies among the system, and then we're going to add some extra information, okay? So for example, we're going to list, our list of annotations will have a description of which versions we're going to care about for this particular test process, right? Because, for example, GCC has a lot more versions than this, but we can define which ones we care about. And we're also going to define some constraints. And I'll just give you one example, one simple example. If you have, if a configuration involves the GNU Fortran 95 compiler version X, then it must also have GCC, the GNU C compiler version X. Okay, and there are other kinds of constraints that talk about, this component, this version needs that component, needs that package, version 4.0 or above, et cetera, et cetera. Other kinds of things like you might see in the Linux RPM package type thing. Okay, but so basically we've now got, we know what the components are, we know what the dependencies are, we know what the versions and constraints, et cetera. So basically we can just fill out this model with all the possible configurations that this set of components could get into. So I'll just show you one here. We basically have, in this case, one version of Intercom. It's going to be built, in this particular configuration, it's going to use PVM 3.45, AP 079, MCH 1.127. And just to point something out here, for example, in this particular configuration, because there was an OR here, my pointer is disappearing, we're going to use MCH, we are not going to use LAM. Okay, so this is just to show you the OR here. All right, so if we basically, go through that and exhaustively fill that out, we have 3,552 total configurations. On the machines we had back at Maryland, it was taking us about 3 hours to compile each one, all right? So if you did the completely naive thing here, it would take you 10,700 hours to compile all of these configurations. That's only 445 days, okay? That's not gonna fit in a nightly build process. Okay, but okay, that's the naive approach. We don't have to do the totally naive thing. So what we obviously can see here is that a lot of configurations share certain subsequences, and so we don't have to recompile the subsequences all the time. We can share those. Okay, so what we do is we take all the configurations and we combine them into a data structure called the prefix tree, and basically our 3,552 configurations are represented here. So basically every leaf in this system is IC version 1.5, okay? And if you work backwards from the leaves, you see all the different things that have to get built up to this root, which is in this case the operating system and its Fedora core that we're going to use in this particular example. Okay, so let me just kind of zoom in there. You've got, for example, the root is Fedora core 4.0. This particular branch has GCC 4.03. And here you split, right? So in some configurations, the next thing you build is the PGI Fortran compiler. In other examples, in other configurations, the next thing you build is the GNU multiple precision number package, okay, of version 4.21, okay? But the point here to point out is that, the Fedora core and GCC, that work can be shared among everything that flows out from there, okay? So this gives us basically a very simple, picture of everything that has to be built, and we can basically build, everything here by walking the tree, okay? And when a client comes in and says, what do you want me to do? I'll just grab one of the nodes in the tree. I'll say, here, take the node, give you everything, the subpath back to the root, all right, and say, here, go build this, all right? And I'll have them build that in a VM, all right? So they can build it, stop. And then, if anybody else later wants to build on top of that, basically wants to build a child of that subpath, then they can just grab the VM that's been stored and start working from there. Okay, so we can share or reuse some of the work. Okay, all right. Now we implemented this. We have a client and server, works with VM, etc. We also built a simulator because as we're playing with lots of different parameters, it's easier to run the simulator than it is to run this. So this next result comes from the simulation, not from the actual. Not the actual data, but basically if all the configurations build in this tree, okay, with 8 machines using 8 that can cache up to 8 VMs apiece, exhaustive testing now takes only 355 hours, only 14 and a half days, okay? So that's better. It's not 445, but it's still not, nightly build stuff, okay? So we're going to go another step further and try to think of, well, what more can we do to sample in an intelligent way, so we don't have to build even all this, all right? And what we basically do is we're going to basically use this tree, and we're going to define what we call direct dependencies. So basically, you know, in my CDG, if I've got a component A and a component B, and there are no component nodes on the path between A and B, all right, then I'll say that A is directly dependent on B, all right? And the basic idea here is that if A is going to fail to build, it probably matters most that it's built on B, and not that B happens to be built on C, which is built on D, which is built on E, and some version of F is going to cause a problem, okay? Now, that's not a guarantee. There could be situations where something could go wrong, but this seems like a good heuristic that we wanted to try out. Okay, so let's go back to our picture. One example direct dependency then is PVM here, okay? Oops, come back. Depends on, has an AND node and some other things, but one of the things it depends on is the GNU Fortran 95 compiler, right? And that's because we have a path from PVM to GF with no intervening component nodes, all right? For example, PVM does not directly depend on the multiple precision floating point library, right? Because there's the Fortran compiler in the middle, okay? So, all right, so how do we build this sampling approach? Basically, we're going to go through this graph, and we're going to find the direct dependencies for every component in the graph, okay? We're then going to we're going to identify all valid instantiations of those direct dependencies. So basically, we're going to say, what are all the possible version combinations that, you know, that could instantiate this direct dependency, and we'll make sure that it doesn't violate any constraints. So now we have a whole list of version combinations that need to be built. I need to build A1 on B1. I need to build A1 on B2, A2 on B1, you know, or whatever, this kind of stuff. And you got to keep the ands and the ors straight on this as well, okay? And I've sort of glossed over a lot of those details for right now. Okay, but given that set of version combinations, I'm then going to basically select or compute, hopefully, a small set of configurations that covers all of those version combinations and direct dependencies that I just talked about, okay? So now what I've got is a direct dependency test suite that's hopefully a lot smaller than the exhaustive one. So here's what I had before. With this direct dependency approach, I hope everyone can see the red here, but in the direct dependency approach, only the red ones now need to be built to cover, only those configurations need to be built to cover all the direct dependencies. So I'm going to run this tree instead of the big fat bushy tree I saw before, okay? And you know, now basically we only are going to run 211 configurations that involve about 650 unique components instead of, you know, 3,500 that involve about 10,000 components, all right? We did this, basically we saw that no loss of effectiveness in this particular case. Anything that we could expose, any problem we could expose with the exhaustive approach, we could expose with the sampling approach. Okay, so that was good. Again, not a guarantee, but that's what we saw in this case. Speed ups, we got some speed ups. In the actual case, we only got a speed up of about 2.54, and basically that's because, you know, a lot of stuff in Intercom doesn't actually build. Okay, so there are some key packages that keep failing, and they're preventing lots of things from being built on top of it. And it turns out that, you know, there are lots of ways that you can't build Intercom. Okay, now as they fix those, or as things get improved, you're going to have more opportunity for savings. So again, using the simulator, if everything had built, we would have had a speed up more on the order of about 15, because it would have taken, you know, 52 hours instead of 355. And again, the point here is that if nothing builds, well, you don't save anything by doing less work, right? If nothing works, nothing works. All right, but as they do more and improve the system, the improvements will become more apparent. Okay, partial summary at this point. Infrastructure's in place and working. Like I said, we've got a client-server implementation. We use VMware to cache our VMs or store our VMs. We've got a simulator for exploratory analysis. By the way, that's partial summary. That's not we're not done yet. The initial results are promising, but we've got a lot of work left to do. In particular, we know that we don't have the best algorithms for computing the direct dependencies at the moment. We know we don't have the best algorithms for choosing the right configurations. We've got to do some more work there. Also, we don't know what optimal is. Theoretically, we're not sure what the best we could do is at this point. So we don't know how far off from that we really are. So we've got a lot of stuff to do here. And clearly, we want to apply this to more systems. We're always looking for volunteers. Okay. Let me go on to a second piece here. excuse me, basic, so this is about configuration level fault characterization. So the last one sort of focused on builds. Now we're going to get into a little functional testing. Again, the deal is you've got faults. They're related to configuration options and settings and combinations. We want to uncover those. We don't want to run everything. So one approach we've used in the past is to use a mathematical object called the covering array to basically find a small sample of configurations that we ought to run. We're going to test just those configurations, and we're going to find out, in which parts of the configuration space regression tests are failing. Okay. Once we've got that data, we're going to build models that help us to characterize what those problems really are. So I'm going to focus now on this covering array part, the part that says how do we do the sampling. Okay. The way we've done it in the past, and the way other people have done it, is you compute this thing called the covering array, which basically is a set of configurations. So if you have a T-way covering array, or the strength T, which could be like 2, 3, 4, 5, whatever it is. A T-way covering array is a set of configurations in which all ordered T-tuples of option settings appear at least once. So basically, if I'm talking about a two-way covering array, what I want to know is that for any pair of options, all possible option settings are covered. So this is sort of this is a kind of interaction testing approach that we heard people talk about earlier today. So let's say we've got this example here. We've got a system with 3 options. Each option has 3 values, 27 possible configurations. If you pick these 9 that are here, you have a two-way covering array. And what does that mean? So let's look at options 01 and 02. You've got you got 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, etc. Okay. If you look at 02 and 03, you got 0, 0, 0, 1, 0, 2, 1, where to go? 1, 0, 1, 1, 1, 2, etc., etc. And the same thing is true about 01 and 03. So basically, by just picking these 9, you've covered all pairwise combinations of option settings in the system. Okay, so we're not going to run them all. We're going to run a subset, but it's a systematic subset that happens to cover these interactions. Okay, so people have done this. There's been a lot of work on this. But the dirty little secret here is, in order for you to do this, you've got to pick T. You've got to say, is it 2-way, 3-way, 4-way? What am I going to do? And you've got to do that before you actually build the array, right? You got to know what you're aiming at. Well, practically speaking, I don't have any real basis, theoretical or historical basis for predicting what T ought to be. Okay, I'm just going to pull it out of the air. Okay, in fact, our experience, some work I'll talk about later with MySQL, we see on a daily basis. Sometimes the problems are easy. They're one option explains them. Sometimes it's 2. Sometimes it's 4. Okay, and it goes back and forth. So there's no good a reliable basis for picking what T should be. And the reason that's important is because if you pick wrong, there are some costs involved. All right, if you pick T too high, you're going to build a big array. Okay, you're going to run too many tests or more tests than you absolutely need to. And if you're in a constrained situation like a daily build process where you've got to finish at a certain point, you might not finish. Right, and if you don't finish, you're going to have these big gaps in your data. You're going to have a bunch of holes in your data, and when you go to try to characterize what's causing the failures, this is going to impact your classification performance. Right? Basically, you're going to be able to make mistakes because of this. Same thing on the other side. If you pick too low, again, you've got a problem that involves 3 options, but you've only looked at every pair. You've got holes because you haven't seen all the 3-way combinations. That's going to impact your classification performance. And so what you're probably going to have to do is just start from scratch at a higher level. Okay, build a bigger array and start again. Right. So none of those things are good. So what we have come up with is an approach that we call, incremental covering arrays. And it's basically, the basic idea here is we start with a traditional array, we execute the test, we observe the failure. So we're going to start at a low strength, maybe 2, build it, run it, classify, and if we have more time, or if our classification results aren't very good, we will increment T, and we'll just start over at 3. Okay? Now the thing that's different here is that we're going to build the new array out of the old array that we've already run. So we're going to use the old one as a seed, and we're going to build the rest of the new array around it. Okay? So just give you an example here. If we have one array per level, we might start with this array A, which is a 2-way array. We run it, we decide to do more, we'll go up to 3. Okay, well now the 3-way array is A plus B. So we took the old stuff we already did, filled it out with B, and now we only have to run B to get a 3-way. Okay? If we have to go up again, take A and B as our seed, fill out the rest of this C, and then A, B, and C become the 4-way. Okay, so that's sort of the idea where we can reuse things from before, and then we'll talk about whether that actually works or not. If we're going to use one array at every level, that tends to be good if the faults are deterministic. Okay, if they're not deterministic, we may need to do more than one observation per point. So we might have to do multiple covering arrays. And so just want to show you here that the same idea of incremental arrays can be extended into multiple arrays per level. Okay, I will skip over, I'm sure you're glad of this, so I'll skip over the details of that, but you can see it in the paper, and it's a pretty straightforward idea. Okay, so does this stuff work, right? How does this compare to traditional covering arrays? So we have been doing some work with folks at MySQL, and basically, you know all about MySQL. It's a big system, continuously evolving, geographically distributed, developer-based, dozens of configuration options, runs on bunches of different OSs and compiler combinations, et cetera. Okay, so we took a release 5.0.24. We just looked at 13 of these configuration options that each one had between 2 and 12 settings. So there's a total of 110,000 unique configurations in this space. Okay, and then mostly for fun, we basically ran 460 regression tests over each configuration on a grid of 50 machines, and we basically let that run for about 6 months, and just did it. Okay, that was really, I don't know, more for fun than anything else. Just more as a test of our tools, okay? But at the end of the day, we actually know what's going to happen with every one of these configurations. So this is our base set of data, and this sort of defines the truth for us. We then go and say, okay, well, what if we had used covering arrays instead, okay? And in one case, we built 3 traditional covering arrays, and we compare at levels 2, 3, and 4, for T between 2 and 4. We also used our incremental approach, again, T2, 3, and 4. And you can see that, for example, the traditional size, so the incremental size at the beginning is a little bit bigger. It's 100, basically it was 108 configurations for the traditional approach versus 113 for the incremental approach. But then when we go up to level 3, with the traditional approach, we have to generate 324 new configurations, whereas with the incremental approach, we only have to add another new 223. Okay, so our three-way array is actually the first 113 plus the next 223, but we don't have to run the first 113 because we've already done that. Okay, basically, how well did that work? Well, the incremental approach exposed and classified the same failures as the traditional approach. We didn't lose anything by doing this, and the cost of using this approach basically sort of depends on T, and it depends on what the failures actually are. Okay, which you don't know before you start. But if you pick T right, okay, if you get all the failures are at level T and you pick level T and you go, the incremental approach is going to cost you a bit more. Okay, in fact, in this case, it was between 4 and 9% more for 2, 3, and 4 four-way arrays. Okay, I mean it's actually not that much, but it was a little bit more. Where you win though is if you guess wrong. Okay, so if you pick T high, okay, and the failures are actually fairly simple, you're going to do a lot more work than you should have. In this case, it was anywhere between 65 and 87% more work, okay, by picking too high. Okay, if you pick too low, then remember you're going to have to basically do the lower one and then increment up until you find everything. And in that case, again, the traditional approach, both approaches will move up, but the traditional approach doesn't reuse anything. So the incremental approach basically saved between 28 and 38%. Okay, again with no loss, so it cost less with no loss of effectiveness. Okay, another partial summary at this point. So we've applied this process to a configuration space with over 110,000 configurations. It was also partially a test of our tools to make sure our tools worked and were reliable and this kind of stuff. So that was nice. We found many test failures corresponding to real bugs in the system. Again, that's good. In terms of our incremental our covering array approach versus the traditional approach, I would say that the incremental approach showed itself to be much more flexible. Okay, much more appropriate for a daily build type process where things are changing and stuff like that. And we really do want to run the minimal amount of stuff that we actually have to. It appears that, at least in this case, it offers substantial savings if you made the wrong guesses in certain cases, while incurring a very minimal cost if you guessed right with the traditional approach. Okay, so basically for like 4 to 9% insurance, you're basically going to do better, I think, with the incremental approach than the traditional approach. Okay, so the other thing that I want to talk about with respect to this work, which is kind of breaking news, is that we've been working with the MySQL guys. We've started a a Skoll continuous integration build and test process for MySQL 5.1, and we're now ready to turn this over to the world. So we basically now have whatever it is, 50 machines at Maryland, and I think as of about 30 minutes ago, one developer machine, where we can basically where clients can download our software and become part of our distributed experiment. Okay, so you can, if you're someone who's comfortable having sort of build processes going on your machines, you can download our code. It will call into the server, download MySQL 5.1, build it in some configuration, send us back the data, and we'll keep going. And so we're going to try to see how many people we can get to participate and see what kind of data we can gather, what kind of stuff we can learn about a process like this that's going to be globally distributed. Okay, you can take a look at this. I got this little tiny URL. If you're interested in participating, I encourage you to go to this website, download our software, and participate. Have pity. As I said, it's been working for about 30 minutes, so the things are going to break. I didn't do the demo here. But if you're interested, I'd really appreciate it if you gave it a try and send us some feedback. Okay. Okay, at this point, I want to turn it over to my colleague, Atif Memon, who will talk a little bit about some of his work in test generation. And Atif?
Thanks, Adam. I'm Atif Memon, and I'm going to spend 10 to 15 minutes giving you a commercial on where the heck do the test cases come from. All right? And so many of us seem to agree that the developers should write unit tests. Okay, which I agree with because they are the closest to the code and they know what the code is about. But when these units get put together, then that's where things actually start going wrong. And our experience with Skoll and some of the large systems that we've been working with, these systems are really like 10 million lines of code, but they come bundled with maybe 180 test cases, 260 test cases. And frankly, we are getting tired of rerunning these test cases again and again. So what we would like to do is to actually regenerate test cases or generate new test cases. And the ultimate goal is that something like Skoll will be able to drive the generation of new test cases on demand, the test cases that it needs, and then deploy them, learn from their execution, and then regenerate new test cases from there. All right, so how do I go forward? Okay. All right. So I'm going to present this work in the context of GUI testing. And I've heard from several of you about UI testing and GUI testing, and it seems to be a topic that everybody has some experience with. So I'm going to talk about how I'm using model-based techniques to generate test cases for GUIs. So what I'm showing here is essentially a JFC unit test case, and it's essentially like a test case that puts something in the login field, puts another text in the password field, hits the enter button, and then waits for something to happen. All right, so a tester has written this, and essentially it's following one sequence of events that a user can execute, all right, which is good. Now, what about the other interactions? Maybe there are many ways of doing things, and this is one of the common problems in GUI testing, right? There are so many ways of doing things that it's very difficult to come up with test cases that do all kinds of permutations of events, right? In fact, the number of interactions grow exponentially with length. If you keep getting longer and longer sequences, they actually grow exponentially with length. So instead of using these JFC unit kind of tools, people use capture replay tools. And the problem, of course, there is that you have to capture the sequence first, and then before it can be executed. So that's also pretty tedious. And it's often happened that I have come up with a GUI-based software, and I have given it to some users, and they come back to me saying that, hey, I crashed the software, or your software crashed my system because I did this and I did this and I did that. And I tell them that, hey, you were not supposed to do that because I tested it on these common sequences, and why did you come up with this uncommon sequence? But one person's common sequence is another person's uncommon sequence. So they will definitely do things which will break the system. And that's because we are unable to test the software properly on a reasonable number of sequences. So one of the answers that we have is to do model-based testing and come up with a model of the software and then use that to actually generate test cases. Remember, we are trying to integrate this model-based testing into Skoll. So the goal is really to have a turnkey solution. All right, we don't want to actually shift the burden of writing the test cases and maintaining the test cases to one of coming up with the model and maintaining the model. Because as soon as you hear model-based testing, people immediately think of, okay, do I have to now come up with the model? When my software changes, who's going to change that model? So things become even more complex. So our solution is to actually come up with a model automatically, use that to generate test cases. As the software evolves, we come up with a new model of the new software, generate new test cases. So it's essentially like a throwaway kind of solution, throwaway test cases kind of a solution. All right? All right. So the first step, as Adam has also described, is to model this space of all the possibilities that we have. So he talked about this configuration space and then sampling it. Then he talked about this intercom space where all possible exhaustive paths were modeled first and then sampling. So the first thing we are going to do is to model this event interaction space. So let's try to understand the creature that we are dealing with here. So this is a simple paint application, and I'm showing you some of the events that the user can actually perform on this application. So clicking on toolbars, clicking on the menu button, dragging the mouse on the canvas, clicking on this toolbar. These are some of the events that the user can perform. And we kind of come up with these constraints which essentially say that this event can be followed by this event. All right, so it's essentially coming up with a sequence relationship, what we call the follows relationship between events. Okay? And this becomes what we call an event flow graph. Now notice that all the nodes in this graph are events that a user can perform, and the edges essentially say that this event can be performed after this other event. All right? And the events that have these arrows coming into them are the events that can be executed as soon as the application is first launched. All right, so let's call them the start events. So in this model, the events, the nodes are representing the events, the edges are representing the follows relationship, and once you have this model, you should be able to generate test cases. Now the good thing about this model is that we are actually able to obtain it automatically from an executing software by using reverse engineering techniques. All right, so you give me an application, I can reverse engineer it, and I can create this event flow model. All right, so now things are getting slightly better, because what I am asking you to do is to just give me a software, and my tools will actually reverse engineer, generate test cases, and run them. So if you look at this model, what we can do is maybe traverse it in a random fashion, start from one of these events that are available to us in the beginning, and then take the next adjacent edges, keep traversing this graph, essentially like a monkey, and spit out these event sequences and run them. Okay? And there are many tools that are available online that actually mimic the monkey way of testing, right? But now that we have this model, we should be able to do something slightly better. So what we are doing is sampling this event interaction space and coming up with what are essentially adequacy or coverage criteria on this graph. So for example, in one of the papers, we showed that if you cover all the edges or generate test cases that cover all the edges, then you actually get much better fault detection effectiveness than random traversal, right? And how would you generate test cases that cover all the edges? You essentially pick an edge, take the two events that are adjacent to this edge, all right? And then start from one of the start events and use the shortest path algorithm to get to this first event, and you essentially have a test case that's a length 3 test case because it has 3 events in it, and it can be run automatically on the software. Okay, so these are our two-way covering test cases because they cover each edge and each pair of events, and they can be automatically run. Okay, so how does this work? If you look at our tool, you can actually point to the CVS head of your application and push a button and then read the error report saying that this test case failed, these test cases failed. All right, but actually what happens is it gets the code from your CVS repository, builds it, reverse engineers it, generates these test cases that cover all the edges, essentially the way I described them, and runs them. So we went to sourceforge.net and picked out 4 applications that are reasonably heavily used to see how our process worked. And using this process that I have before, okay, I need to go up, yeah. For Crossword Sage, FreeMind, GAN project, and JMSN, we found 5, 4, 3, and 3 faults in this software. We reported some of these faults. The developers actually went and fixed some of them, saying that they were relevant faults, and they were faults that others had not actually found until then. So this gave us what our goal was, to give a turnkey solution to test case generation and execution. But of course, we know that there are certain kinds of errors that we are not able to find because we are essentially generating these short sequences that cover all these edges. So we're going to use this Skoll philosophy to actually generate longer sequences. All right, so I'm going to kind of give you a very intuitive flavor of what that means. So what is the reason for us not generating these longer sequences? As I said, the number of test cases grows exponentially with length. So as soon as you get from length 2 to length 3, you're talking about a million test cases or 10 million test cases. All right. So what we decided to do was look at the GUI and see that there are certain events that interact with each other. For example, copy, paste, cut, all of them seem to be sharing the clipboard, so they interact with each other. Other events like save and find probably don't really interact much, all right? So because their functionality is very different. So what we should really do is to identify these interacting events and break up our event flow graph into smaller graphs and generate longer sequences for these smaller graphs, all right? I'll describe what I mean by interacting and non-interacting in more detail. So once we have identified these interacting events, we will mark the edges for these pairs of events that are interacting, break up the event flow graph into different parts. So this is a cluster of events that we found to be interacting, and then essentially take what is a transitive closure of this graph and generate these longer sequences for each of these clusters, right? So what is an interacting event? Remember, our goal again is to keep things automated, all right? We don't want a tester to go and say that this event interacts with this other event. We want to keep everything automated. So we observe how events execute on the GUI, okay, first, and then we examine if one event had any effect on another event's execution, all right, by extracting the GUI state and observing how things changed, all right? So for example, I execute event E2, let's say it's the find button in your GUI, and then I execute an event sequence called E1, E2, all right? So E1 might be select a text field, and then E2 might be find. So did the execution of E1 have an effect on what E2 did? If it did, then these two events do interact, all right? So I annotate the graph. I say these are interacting events. So the first thing we're going to do is to generate our two-way covering test cases, which is the process that I described before. Call that the seed suite, throw it on the application, let it run, and then collect the runtime state of the GUI, find these interacting event sets, and then generate more test cases that are 3-way, 4-way covering, run them back again, and keep repeating this iterative process until you find no more bugs or you run out of time. Most likely you'll run out of time. All right, so this process again was completely automated. So we wanted to see if we did better than our 2-way coverage approach. And we did, because we found 3 more bugs in the first 3 applications and 1 more bug in JMSN. Okay? And we actually examined these bugs, and we knew that we found that we could not have found them using these shorter sequences. So these really required long events.
Sorry,
Okay?
quick question. How did you decide that you'd found a bug?
Yes, I'm coming to that. That's a good question. Yes. All right, so I'm going to give you a partial summary, and then Adam is going to sum up the whole thing. This is like one of those movies that never ends. You see it ending several times. All right, so I talked about the JFC unit. I showed you some of the test cases. The good thing about those test cases is that they can be replayed by a robot, and there are lots of these robots out there that will execute test cases for you on a GUI. So we actually use some of those things. And I showed you that the number of interactions are too large to test. So I came up with a model of all possible interactions, and then using the same Skoll philosophy, try to sample the space. So now if you think about this Skoll approach, we are generating this initial test suite, and the Skoll server essentially is coming up with this model and then generating this suite, sending it to the Skoll clients. Each client is executing the test cases, sending the results back, and the server is annotating the model and then throwing more test cases out to the clients. And the process continues. The way I kind of described it was I gave you the success stories. Over a couple of drinks, I can describe the failures. But your question was that how do you know a test case fails?
Yes.
Right. So for the time being, what we've done is, since we want everything to be automatic, we don't want anybody to specify a test oracle for us. Any test case that crashes the system is a failed test case. And there are some assertions in the code. If the developer has been good enough to put assertions in the code, whenever we find an assertion violation, we say that there's a problem here. Okay? And this actually brings about an interesting point, that there are some things that can be fully automated. All right, so what we've done is we have identified those things, and we have tried to put them in a very tight, fast executing loop. Okay, so whenever somebody checks in code, GUI code, we do this process and we run it fully automatically, and we can do this any number of times because it's really inexpensive. Within a few minutes, you can get some reports. And then there are things that require specification of a test oracle, maybe from software specs. So we have ways of specifying preconditions and postconditions. And if somebody is willing to invest the time in doing that, that process can be run, say, nightly, less frequently. Okay. But in the context of the Skoll approach, we are still just doing crashes and assertion violations. Okay. I'll be around to answer more questions. Let Adam sum up the presentation.
Okay. Let's just get this thing done here, okay? Anyway, thank you very much. I think I just want to say a few more words about some of the things that we're doing here for future work, and just reiterate a few things. Again, we're doing this, our MySQL build farm initiative, our community build process is starting. Love to have some volunteers, love to have you tell your friends, have them volunteer, et cetera, et cetera. And I'll just put the URL up there again. We're also, one of the great things I got out of this conference last year was contacts with people, the MySQL folks and some other people. We're interested in talking to other folks. If you have systems or that you think might benefit from our techniques, we'd love to talk to you. We're working hard to continue improving the Skoll system. Ultimately, we'd like to make this something that is, let's say, open source or at least freely available, so people can use that in their own projects without necessarily having to, have us in the middle. This is something that's very important to us. We think there's a lot of interesting work here, on the algorithm side. I think there's a lot of work now that's teaching us how to get more tests done faster. I think there's a lot of, as we do this, we're going to find that even that is not enough, and we've got to start thinking hard about what's the right science, as Patrick said this morning, What are the right algorithms to take advantage of this large resource that we have? And so we're going to continue working on that. We're looking at new problem classes. Can we use these giant distributed experiments to teach us something about robustness and performance? Can we optimize at least certain test suites or benchmark suites? Can we use information from lots of distributed users to say something about configuration, to give advice? If you know that some option settings have to be fixed, but other ones you don't know how to set them, can we learn from the work of other people something, and use that to help give people advice about how to configure their systems? Another thing that's come up recently is we sort of act like cycles are free, right? You got a big machine or bank of machines, we're going to use them all the time. Okay, some folks we've been talking to have equipment in their tests that sucks up, megawatts of power, right? Tests are not free. Okay, what can we do with the data that's coming back to know more about which tests are actually paying off from this other sort of cost-aware perspective, which is something we haven't really thought of up to now. Okay, other things is we need to we're really focused on black box testing. Part of our work with Atif here now is to kind of break things open a little bit, start doing some, getting inside the box a little bit. Can we do other kinds of source code analysis as well? That's another important topic for us. And then finally, again, working with Atif stuff and trying to look at kind of a turnkey solution. Can we expand his work outside of strict GUIs, apply it more to web testing or other kinds of things? And these are some of the things that we're trying to look at. So anyway, thank you very much for listening, and I think we'd be happy to take some questions if you have some.
Actually, I have 3 questions. So I'll try to be quick with them so that not taking up too much time. The first one, isn't the configuration design itself pretty time consuming?
Yes, absolutely. In fact, actually in every project we've worked on, we've had the following situation. Tell us what your configuration model is. Here, it's like this. Okay, gee whiz, this breaks. Oh no, I didn't mean that. So I've got, developers, it's sort of interesting. By centralizing the configuration model, we're actually exposing what the configuration constraints really are, which a lot of people don't know. You get fights from, 2 different developers. One says this is legal, one says it's not. Nobody knows. Things used to be legal and they got, changed, and nobody updated the models. So it's very much of a time-consuming process. But we found that actually to have a lot of payoffs also for the developer to sort of centralize and manage that configuration information, because otherwise it's just sort of in people's heads.
And on the 2 ways,
Yes.
Six Sigma has rules of thumb around experiment design that they use. Have you guys seen in practice that your results are similar to the rules of thumb, or is that why you're doing so much research around it, because it's totally different?
Well, so we've done some work that actually uses experimental designs as opposed to just a covering array, which is meant to cover things for performance measurement and some other stuff that we talked about last year. And I can give you some information offline. But basically, every one of these processes has sort of different assumptions and different needs. And you can't, you have to be careful if you just sort of roll out some of these rules of thumbs and standard designs, because they may not fit. And in fact, that's actually one of the reasons why we work with statisticians at the National Institute of Statistical Sciences, because they can help really bring a lot of a lot of their expertise to bear on how you define experiments and things like that.
And then the last one, with the automated test design, I could see how that works in terms of boundaries, in terms of your test execution, but you guys said you didn't want to create an oracle. How's that working with really data-driven stuff? Is that where a lot of it falls down? Because if you don't define boundaries on the data that you're putting in, say you log in and these kinds of things, is that where it crashes often?
No, actually, we found that lots of times interactions that the developer actually never anticipated seems to cause most of the crashes.
I have a question regarding the test case generation. So you're reverse engineering the software automatically and identifying interactions automatically in the code.
Yes.
So can you tell me what you would consider an interaction in, for instance, a Java app?
when I say interactions, I'm actually the edges in the graph that I showed. Essentially, they say that an event can be executed after this other event. All right. And
But how do you identify events in the code?
that we use Java API to actually extract from Java Swing widgets things that can be that have event listeners associated with them.
So it's anything that could trigger an event?
Yes.
Okay.
And by the way, the interaction is defined empirically. So you say, well, if I start in a known state, I do an operation, I get to another state, and now I run a two event sequence. Do I end up in a different state, right? Or did it not have any effect? And so he's using an empirical method of testing and saying, do I observe any interaction between these two events, yes or no, and then marking them.
Two questions. One, obviously, as you were saying, you don't know what actually is a failure per se, but for example, if something in the tree generates, let's say, a 500 error on a web page, is that considered a failure by the idea of, well, it broke the system, or is a breaking of the system actually, the whole system actually crashed?
You're speaking about the GUI testing?
Yes.
Yes. In our case, did the system crash?
So like a 500 error being generated by the site itself wouldn't be considered a crash of the system per se.
Right. I mean, currently we're not doing web testing, but if you wanted it to be recognized as an error or a failure, then it could be.
Which, that leads me to my second point is, in the model that you create, how would you allow someone to, when they see all these results, then say, okay, I want a 500 error to be considered a failure, or I want a 404 page to be considered an error? How would someone have to manually go in and put that information in for those tree iterations, or would it be something that they could just say, okay, I want that, anytime you see a 400 error, that's an error, and that should fail?
Oh, so what we do is we specify actually what are called mini oracles. And so for each type of error, we define an oracle. So we say that if the 400 error is an error, then we say that somebody has to go and code that. So it will be customized for each application.
But it can be customized on the whole instead of for each
Sure.
Okay. Two questions and a remark. So I'll start with the remark. It seems obvious that that kind of generating the model by reverse engineering will not allow you to find errors that are due to edges that are actually missing or that should be there, or that are there and shouldn't be there. My real question is, it looked pretty impressive to find, okay, there are so many bugs in an open source system. How much testing of the system was actually done?
So these are actually, SourceForge reports the activity percentages for all applications. And these were like among the top applications that were implemented using Java Swing. I mean, all of them were like 99 point something % activity usage.
But
So
how many tests were actually done? Because I guess these defects that you found were not on the straightforward usage passes.
So for this experiment, I think we probably might have generated and run close to 10 to 15,000 test cases.
And tests by like unit tests or
These
other
are
kinds of
sequences
tests?
of events.
Okay, so there were no tests done by other people on that software before. The other question is, sometimes I'm having events that change my user interface, but can't be triggered through the user interface, like a network error or whatever. How do you deal with these kind of events?
So in this particular experiment, we did not deal with them, but the event flow graph can be actually enhanced to add those events in there. Okay.
Thank you.
Sure.
That is a manual
Yes.
event flow. That's a manual.
Hi, I've got one question. You are talking about the MySQL branch farm. So basically, you may want to check out or download the MySQL source code, build it, run your unit regression test. And do you have some tools to parse all the logs and display them to have a global overview quickly, like a dashboard or something like this?
Okay, so we have built parsers for the tests, okay? In fact, actually, the test that MySQL distributes has its own reporting of whether there are errors or not. So we can just basically parse those things and decide whether we've seen a failure or not, okay? Right now, we have very rudimentary visualization. I think we use tree maps. I don't know if you know what tree maps are, but this is one sort of, I don't know if you've ever seen I don't know if they're actually named the people, but there are various kinds of visualizations for looking at these sort of classification type problems, and we use some of those. But it's very rudimentary. So the visualization stuff, we're hoping that, in fact, other people can contribute that for us. So we're going to put the data in the database. The database will be accessible, and we hope the community will, people write the visualizations that they want for their own error reports. Okay.
Thank you.
Since your graph is designed by reverse engineering the code, is it possible to find path of error that depend from graphical interface that are dynamically generated?
That's a very good question, actually. Most of the work that we've done is with static GUIs. When lots of widgets are generated using, for example, reading data, or the GUI changes as it's executing, then we have difficulty. Because when we are doing the reverse engineering process, we actually take an instance of the GUI and we take a snapshot of that and then reverse engineer the widgets out of that. It may be possible that you can execute some other path in the GUI and get additional widgets that we have not seen. So for that, what we have is essentially an event flow graph editor that a person can actually manually add widgets and nodes in there.
And it is possible to prune part of the graph. For example, if you have cycle, like in the picture that you were showing before, there was a palette of commands that were changing the state of that application. So probably having a sequence that was pressing some of them were like useless. I mean,
Right. So, for example, if there's an edge from file to file, you don't want to keep pressing file again and again, because it probably doesn't make much sense. But then that's why we have restriction on length. So we will do it twice and that's it.
okay, thanks.
I have a question. I heard you speak of pre and post conditions. Are you able to generate assertions based on expected behavior?
So we manually specify pre and post conditions.
Right, and then are you able to generate assertions or expected behavior from that?
You mean Java
test.
assertions and embedded in the code?
Yeah.
We have not done that yet, but our test case replayer actually reads the pre and post conditions and then uses them as essentially like assertions.
Oh, I
But
see.
one could actually probably embed them in the code.
Okay, so it'll fail if it doesn't match the pre or,
Right,
I see. Okay.
As far as minimum attributes for a system being contributed to the Skoll grid, are there particular things you're looking for? You mentioned Fedora Core. I'm just interested if there's particular types of machines or operating systems you're looking for minimum kind of server contributions.
Let's see here. No, not really. I mean, we're willing to talk to anybody, basically. But I think if for example, if you have your system runs on one operating system, you have no configuration information, you don't. There may not be. I mean, there's certain situations where it's probably not worth your time to get involved in our stuff. But I mean, I think if mostly we're really right now focusing on situations where you've got lots of moving parts, and there's just this combinatorial explosion in the number of things you have to test. And so if that's the kind of thing that you see, we can model that. And I use the word configuration a lot, but it doesn't have to be your standard configuration options, right? It could be, it could be other kinds of parameters, policies, location, it could be lots of different things like that. But I think the real test is, are you experiencing a combinatorial explosion in the number of things you need to test? If so, then we'd like to talk to you. Okay?
Yeah. Even the event flow graph by itself is one of those models.
Right.
So I noticed that one of the applications you tested was FreeMind, and as you use FreeMind, you build a map, and the pieces of that map are clickable. But if I understand you correctly, you start only at the initial state of the application, and what you're building inside is invisible.
Right.
Okay.
In this case, we also started FreeMind in different start states. So it loads the map before it actually runs anything. So we have something up there that can be clicked on.
I was just wondering on the Skoll, when you were actually planning on open sourcing it, if you were. I mean, that's the question mark behind
Right,
it.
so we, basically, we've used everyone, we sort of try to use our collaborations as forcing functions to expand things and to make it more usable and stuff like that. So now that we've finally gotten this thing with MySQL going, people are going to need to be able to download our clients. So now we have to, we have to have something that runs outside of our own our cluster, right? So, basically, as we start to grow these things that we're like not ashamed to have, seen, we're going to start making those things available. Because what I really want is to build up a community of people who are doing their own processes in their own, not with me in the middle, right? But doing their own things in their own companies, in their own communities, and things like that. So I don't have a timeline in my mind right now, but this is something that we're starting now with this MySQL thing. We have at least a client out now, and we want to start to continue to keep pushing the rest of the server out. We're always looking for volunteers. So.
The only reason why we don't share code is because we are embarrassed to share it. Graduate students are very bad programmers.
So Adam and Atif, thanks very much.
Very much.